Right, next contribution is from the University of Manchester, and David Harris is going to give it. Thank you very much.
Okay, thank you very much indeed. I hope you can hear me at the back. If not, there's a nod. Great, okay, thanks very much. Okay, in a sense I want to do, I think, the very opposite of what Bob did in his last talk. I mean, basically he sort of looked very carefully through a lens at each individual grain. And what I would like to do now is to take that out of focus so that we can no longer see individual grains and we have to look really at the whole macroscopic system. So really I want to look at very large granular systems, if you like, with very small grains. So I can go to a continuum limit. And although in talks I find that I can't say the word, this is a phenomenological approach. Okay, so we're doing something slightly different to the previous talk, and also most talks here really have been not on the dense packing, but on the dilute flow. So here, just as in Bob's talk, we're certainly dealing with dense systems. It says the word slow there. I had been hoping to sort of move out a little bit into a faster regime, but in the end I decided to keep that word slow in, hoping to make it go slightly into a faster regime. We'll see how that comes up later. Perhaps I should apologize. This talk is very wordy. It's the way it came out. It's too late for me to do anything about that now. I want to talk about a new plasticity model, which I call the double slip and double spin model. If you're familiar with the double shearing, that corresponds to the double slip. In fact, the double shearing model is a double spin model, but it just doesn't emphasize that. And there is another model called the double sliding free rotating model. All these, if you like, are part of a family of models. And I also want to link it to the traditional plastic potential model. And what I'm hoping to do is to convince you that somehow the double slip and double spin model escapes some of the difficulties associated with both the double shearing and the plastic potential model. Okay, well, let's just see how we go. I guess, well, first of all, I'd like to thank the IMA for some financial support, and I would like to thank Dr. Wildman for the help that he gave me over the last few weeks. I would now like to, I guess, repeat some of the things that Rafaela said in her talk. Trying somehow, at some point I was trying to move slightly away from the slow regime, if you like, use a slow model, but move slightly out of that way, which made me think in terms of solid-like and gaseous-like states, which I guess are pretty well defined. But then the plasticity state somewhere is in the middle, you know, sort of a liquid or plastic-like state. Maybe this is more ambiguous, not quite easy to define that. And so somehow plasticity models occupy a middle ground between a nice, definite, solid-like elastic model and the more gaseous states. And somehow, where is the dividing line? Well, I guess the dividing line has to be the constitutive equation for plasticity models is rate independent, and for the fast flow, it becomes rate dependent. But nevertheless, I did try to think about how one could move from one to the other. And so you have, if you like, constrained granular systems, you know, strong walls holding them in, and then you can imagine loosening the constraints so that it becomes unconstrained and the grains can wander apart. And so one can imagine almost a continuum like set of states in that case. And you can imagine sort of dense packings moving to looser packings, moving if you can then input some energy into some kind of dilute suspension. So somehow there seems to be some freedom in the middle of things going on. But at some point, you come back to the idea that really there are just two states. Somehow it's bipolar or it's off-on. And so if we think in a few of those, if we think in terms of sort of kinetic energy fluctuations, they're either insignificant or they're significant. Or if we think in terms of the separation of the grains, I mean, either the grains are touching and there's a zero mean free path, or they're widely separated and it's non-zero. So it's that somehow we're moving towards an off-on type situation. And if we think in terms of forces, then they're either bouncing, there's either collisions, or they're in contact for some time, and so it's going to be sort of non-impulsive, finite duration versus very short, impulsive forces. So again, these things seem to be either or. And although one can imagine sort of clusters of grains having one type, and then these clusters bouncing together. Nevertheless, there does seem to be some idea that it's either one or the other. And so again, the grain contacts can either be collisional or sliding and rolling. Then finally, I guess with this idea of this, if I could call it a bipolar relationship, I guess I went one state too far and I talked about external energy input into the system being insignificant or significant. Then I realized I didn't quite know what that meant, but the idea is that if you have a box with grain sitting in the bottom, then okay, the box is having an important effect, it's holding the grains up. But that's completely different to shaking the box up and down and then turning the solid-like state into a gaseous-like state. So somehow I do have the idea that this division, these two types of state, somehow corresponds to an instability. That, the system is going to collapse, from a fluid-like state down to a solid-like state. And so I'm going to stay really with the slow flow. But maybe we could allow in some rate dependence a little bit by looking at bringing in some inertia, either rotational inertia in particular or even indeed translational inertia. So maybe I can move away a little bit from the very slow flow that we normally think of for plasticity models. So again, I don't want to go through all these, but one can identify certain correlations between the slow flow regime and the fast flow regime. And really this is just summarizing the things that I've mentioned before. And we're definitely going to stay in this solid-like state. But we have a very large system of very small grains. And so I am going to take the averages and not consider the fluctuations. We're going to look at traditional constitutive modeling. Okay, so for a mathematical formulation, just to get the notation going, we're going to choose, as usual, a rectangular set of Cartesian axes, OXI. The Eulerian description will involve both the velocity, if you like. We can average the velocities of, we can take an RVE, average the centers, the velocities of the centers of masses of the particles, and we can also average the rotations in some sense. And because of the finite size of the grains, I'm going to assume that, if you like, a material point acts a bit like a rigid body. You could call it a material point body. So that there is some resistance to rotation. There is some rotational inertia, if you like. So not only do we have V, but we also have the intrinsic spin, omega, which is also a vector. And for simplicity, I want to consider only planar deformations. So we're only going to have two velocity components and just the one intrinsic spin component, which would be the omega 3. So V1, V2 are non-zero, omega 3 is non-zero. All quantities independent of x3. And notation-wise, we'll use Cauchy stress, and I'll use sigma for that. If necessary, the couple stress we'll call mu, but I don't really believe that couple stresses are significant for granular materials. There may be people who disagree with that. I'm going to get rid of the couple stress at the first available opportunity. But we will have a density and also a moment of inertia tensor I, and also maybe body force and maybe body couples. For the equations that are going to come up, the next bit is very important. The fundamental kinematic quantity, of course, is the velocity gradient, dvi dxj, and the symmetric and antisymmetric parts will crop up all the time. I'm going to call this the deformation rate, and it's d. So whenever we see a d, it's the symmetric part of the velocity gradient tensor. Whenever we see an f, an s, it's the spin, the antisymmetric part. I tend to use the words vorticity and spin interchangeably, despite there being a half factor difference. The intrinsic spin vector, it's in constitutive equations, it's convenient to sort of convert that to an antisymmetric tensor, so the dual tensor I'll also call capital omega, and there is the definition, so I'll just move from one description to the other really without mentioning it. That's basically our notation. The governing equations, maybe some of these things are not so important, let's move through these quickly. The stress tensor in general will be non-symmetric, so I will distinguish between those. For plasticity models, it's usual to ignore or neglect the inertia terms, so usually there is a zero on the left-hand side. As I say, I'm hoping to sort of keep in a little bit of rate dependence by keeping those inertia terms in. Also, I want to talk about ill-posedness, and that only comes in when we talk of time-dependent systems, so I certainly need to keep that left-hand side through. Because granular materials change their density, the continuity equation will be important, of course, but not something that we need to talk too much about. The rotational motion, on the other hand, I guess I should say a few more words about that. For these planar systems, there is only one equation, so the three equations reduce to one. Can write it out in this way. Recall mu was the couple stress. Here is the difference between the shear stresses in the plane. What I really want to do is to reduce this back to the usual rotational equation as quickly as possible. The idea is that, firstly, couple stress is somehow linked into the gradient of the rotation, and I don't believe that's important for granular materials. So I'm going to just sort of cross out these terms, and if you like, just hope that that works out okay. If it didn't, one would have to introduce back the couple stress. Also, for normal flows, I like to think that rotation or spin is only going to be significant at either a rigid boundary or some kind of boundary, or in localization. And I was looking at Bob's discs with the bar across, hoping to see whether there was any net rotation or not, but I couldn't quite see that from the films. And so what I really would like to do in as many circumstances as possible is to ignore the rotational aspect and say that if omega 3 is a constant and if we strike out the G3 as well, then of course we'll be back to the symmetric stress tensor. Omega 3 is a constant. Well, it represents a spin, so I guess if it is constant everywhere, I can sort of choose a frame of reference where it takes the value 0. And so, if possible, I will, without loss of generality, assume, in fact, that it is 0, that I am in such a frame of reference. And nevertheless, I will continue to distinguish between sigma 1, 2 and sigma 2, 1. That's so in case suddenly omega 3 becomes non-zero, then I can easily take it into account. Notice that omega 3 being 0, somehow this is a rotation, but this is a continuum model, so we're talking about averages. So it's not saying that the grain rotation is 0, but merely it averages out to 0. So if if a grain is rotating clockwise, then a neighboring grain may be rotating anti-clockwise by an equivalent amount. So somehow this is an average grain rotation of 0. Okay, so, and it turns out that if one wants to use these rotational tensors in constitutive equations, in order to make them objective, then of course one way to do that is to subtract one from the other. And the key quantity really is the spin minus the intrinsic spin, which I call relative vorticity or relative spin. Okay, this is an objective tensor, the little omega, so it can appear in constitutive equations. It appears quite naturally when one attempts to derive the equations. So because we're in plane deformations, many things go to 0, so that makes life a lot simpler. Even though it's not necessary for the model that I'm going to consider, I will take the OX3 to be a principal stress direction, because to assume otherwise gives rise to rather peculiar problems, and so I think it likely that the OX3 will be a principal stress direction. I'm certainly going to assume that today, but it's not necessary. Now, the constitutive properties of these rate-independent materials are indeed, and in the model I'm going to present today, they are determined by the usual plastic potential function and yield condition. So we'll take a yield condition F. Notice this is a general yield condition F. I'm not making any assumptions as yet about the nature of what that yield function is. And there is also a similar plastic potential function. I want to concentrate on the regime where the stress tensor is symmetric, so I'm going to sort of build that explicitly into the notation. So we're looking at the symmetric part. If we want to definitely include the anti-symmetric part of the motion, then we would have to decide what to do about that. And we could either include the anti-symmetric part in F, or we could have a second yield condition, but I won't do that today. So a yield condition, of course, merely restricts the states of stress that the material can feel, if you like. And this is, although I'm only going to talk really about the plasticity today, this is an elastoplastic model, but the elasticity, I guess, is non-controversial. And when we have equality, the material will flow or it will deform irreversibly. For an isotropic material, then of course the yield function will depend only on the stress invariance. That's not particularly crucial for this talk, but it is a fact. And one point that I would like to make is that really when we consider the system of partial differential equations given by the stress equilibrium equations and the yield condition, then really all the information is contained in this second order tensor when we differentiate the yield function with respect to sigma s. Everything is contained, all the information is contained within that. The partial differential equations merely, if you like, sort of conserve the information given by f. And it's very common, particularly in the double shearing model, to move from the stress tensor sigma ij to a set of invariant stress quantities given by P and Q. And if we have a non-symmetric state of stress, then P, Q, and R become the invariants. If I include in the yield condition the intermediate principal stress, if you like, or the third principal stress, then for these planar rotations, then we have a fourth invariant. So one can use these invariants as a way of characterizing the stress. So we can, in order to show that the yield condition contains all the characteristic information of the model, we can go through and calculate these second order tensors. And then the fact that in these Qs we have the differences and the sum of these stress components, if we're familiar with the stress representation which comes on the next transparency, we can see that with the difference then the P's disappear, and with the sum the R's disappear, which gives a very useful and a very simple representation for the stresses. So in this general state of stress, we can have this representation here. This is a very common thing to do with the double shearing model. Tony Spencer always used this kind of representation, although in his case R would always be 0 and S was also absent. But this will work for any yield condition, not just the more Coulomb type. So this is a general analysis, if you like. And the psi that appears in there is defined in this way. Again, it's defined here for a possibly non-symmetric state of stress. So, but psi is the angle the major principal direction of the symmetric part of the stress makes with the x1 axis. So again, we see a division between, if you like, the symmetric and the anti-symmetric parts of the stress. And again, psi is a very important parameter for these models. Okay, so if I quickly run through then for the yield function, for a general yield function, then we can say that f is going to be a function of p, q, and s. Again, we're only considering symmetric states of stress here. For a more Coulomb material, then s is going to be absent. And I've just quickly run through here to show that the characteristic information is embedded there in this second order tensor from only the yield function f and not the stress equilibrium equations. The angle of internal friction for this system can be defined in this way here. So if you like, this generalizes the more Coulomb definition where sine phi is usually taken to be a constant. So here it's variable. Notice this is a restriction on f. I guess that's an important point to make. That somehow I'm assuming that f satisfies this situation here. So the ratio of fp to fq lies between -1 and +1. So we are restricting what f can be here. And that's crucial for the mathematical structure. This transparency here is to show that indeed the well-known characteristic structure is contained in this second order tensor Fij. And if one were to do characteristic analysis, then indeed the stress characteristic directions for the stress equilibrium equations and the yield condition would be given by this. But we see that F contains all the information, and then when you plug that in to the partial differential equations, they just preserve that information, if you like. And, well, again, for a general deformation, then F will be time dependent, and so we may need the condition for continuum yield, although I won't refer to that again here. We can actually do the same, clearly we can do the same, for the plastic potential G, the second scalar function which determines the properties of the granular material. And again, the second order tensor Gij, if you like, again encapsulate or sums up all the information required from the flow rule. So these are the corresponding expressions with G replacing F, but now we see the angle of dilatancy is defined in this way here, sin nu being minus GP over GQ, where GP, subscript P is the partial derivative of G with respect to P, etc. So we have these two physical parameters, the angle of internal friction and the angle of dilatancy. And again, I guess we're considering regimes or flows of granular materials in which those two quantities are the important constitutive parameters, the amount that the material is dilating and the angle of internal friction. Okay, so again, we can go through this, and again, we see that F and G are equivalent in the fact that we now have some velocity characteristic directions from coming from the velocity field. How much more time do I have? Wow. Okay. In that case, that's amazing where the time goes. Yeah? Okay, so in that case, let me just tell you that the plastic potential model, which can be written in that form here, for planar motions we can write as saying that the dilatation is proportional to the shear rate, and that the stress tensor and the deformation rate tensor are coaxial. So that's one set of equations. The second set of equations from the double shearing model, for incompressible materials we have the incompressibility condition, and then we have a non-coaxiality condition here, whereby, if you like, those directions are forced apart by the rotation of the principal direction of stress, the psi dot. Now, both of these models are ill-posed for different reasons. There is also a dilatant double shearing model, which includes dilatation, similar structure. The reason that the plastic potential model is ill-posed is that ultimately, because the stress characteristics and the velocity characteristics do not coincide. It's a necessary condition that they should coincide. The double shearing model turns out to be ill-posed because of the presence of this psi dot term that we have here. And so, what I would like to do, if I hadn't been so slow in talking, I would have developed it more carefully, is to develop the following model, which is a dilatancy model, a non-coaxial model involving now the intrinsic spin, which in 3 dimensions can be written in this term here. And I claim that this model is well posed. I apologize for talking for too long. Okay, I'll stop there. My apologies for rushing.
We have time just for one quick question. Yes.
Well, I spoke too quickly. Nobody will know what I was talking about.
Okay, my question has to do with the beginning anyway. So, you're perfectly right that the couple stresses can be neglected, at least in steady flows, except near solid boundaries. But that's because you get into rotational equilibrium in the center. But also the asymmetric parts of the stress tensor also are only apparent in steady flows at near boundaries.
Yes.
So I'm assuming that you keep that around for unsteady systems.
Yes.
And Then the question is, it seems to me inconsistent to neglect the couple stresses and keep the asymmetric parts of the stress tensor. And can you comment on that?
Well, can you tell me why you believe it to be inconsistent? I mean, it seems to me
Because
that...
wherever I saw asymmetric stress tensors, I saw couple stress.
Oh, yes, okay. This is true. The standard thing is to have what I call a full Kossar model, where you have the couple stress, a non-symmetric stress tensor, and possibly the rotational inertia, though often they get rid of the rotational inertia. Now, I happen to believe, it's my opinion, that the opposite is true. I mean, I can see rotation. I can see that one can't take the limit, you know, as a smaller and smaller RVE, and shrink it to zero.
Yeah.
So I can't take that limit. So I can see that there is residual inertia, but I can't actually see residual couple stress. Now, so I call this a reduced Kossar model. And I make that choice that I will get rid of the couple stress and retain the rotational inertia. I could very easily reverse that if it turns out that I'm wrong. I don't believe it's inconsistent. It seems to me that it does correspond with what I see in granular materials, and I'm just trying it out to see if it works. But if you know that it's inconsistent, then please tell me
Well,
why.
I don't know because
no,
I've only looked at long-term steady systems, so I
Yes.
can't be. But in long-term steady systems, the two coincide.
Yeah, I'm just going to use this for short-term transient motion. And I'm hoping that for long-term motion, the couple stresses are not important for granular systems, that really a classical model will work.
But I'm trying to remember. I did all this nearly 20 years ago, so I've got to remember these things. But it seems to me, for the same reason that you can't shrink your volume down, then you permit the possibility of there being torques
Yes?
exerted independently of forces, and therefore you admit the existence.
Yes, I do admit them. I just say I hope they're negligible.
Okay. As long as since we're in the Obama era, hope is fine.
I have to live by hope.